And we'll get started. All right, so today we will be completing the last bit of notes for section 9.3. And then we will get through the notes part of section 10.1. We'll do the PowerPoint presentation that goes along with section 10.1, which essentially uses all the parts of what we've seen so far this semester from chapter 6, 7, 8, and 9. And it kind of puts it all together with things that we do with two populations by comparing them. All right, so we'll take a look at that today in the beginning of chapter 10. Yeah, so that's kind of the idea for today. Overall, over the next couple of weeks, my hope is that this week, today and tomorrow, we will get through sections 10.1 and 10.2 as far as notes. Next week, we will do practice for both sections. I think because they're so similar and because it's applying the ideas that we've been working with since chapter 6, I think that that's the best way to kind of practice these things is just put them in together. And it'll also help us review the same kind of concepts that we've done in the previous chapters. So that's kind of the idea. So this week, next week, the following week, I want to take to do AP prep stuff. So there will be some more information that I'll provide you guys that you may or may not see in other classes. I'm hoping to also do like practice AP testing kind of stuff using the AP digital exam app that you guys will need to have. So we'll work with that the last week of April. And then hopefully in May, we'll get through the last couple chapters for the textbook, do some review, get ready for the AP exam in June, and then we'll be done. That'll round it out. All right. So the last bit of the notes for section 9.3 are actually in Desmos. I'm not going to share the link because there's nothing for you guys to actually do. I'm just going to share my screen and go through those last few slides. And I do encourage you to write down any notes that you want to add to your own personal notes and ask questions for clarification if you need. And we're going to get started. So I need that one there. There we go. All right, so boom. All right, so two-sided tests and confidence intervals. This ties into the very last thing that we saw in class last week with our two-sided test. Two-sided tests and confidence intervals are connected quite strongly between when we're dealing with means, more so than it was for proportions. And this is because both inference methods for means use the standard error of the sample mean in the calculations. Right, with our test statistic, the the standard error is the denominator of our fraction here, s sub x divided by the square root of n. And in our confidence interval, the standard error is what we're multiplying by our test statistic, s sub x divided by square root of n. Both of these use that standard error. That's what makes their connection so strong. So what this does is that when you have a two-sided test at significance level alpha, suppose alpha equals 0.05, and a 100 times 1 minus alpha percent confidence interval, 95% confidence interval of alpha equals 0.05, gives similar information about the population parameter. Meaning if I know the parameter exists in the confidence interval, right, then we can start doing other things that these next two checks are about. When the two-sided significance test at level alpha rejects the null hypothesis, the confidence interval, the 95% confidence interval for mu will not contain the hypothesized value mu sub 0. Right, so when we reject the null hypothesis, we're saying that that supposed mean is not in the confidence interval. When the two-sided significance test at level alpha fails to reject the null hypothesis, the confidence interval for mu will contain mu sub 0. Right, so if we fail to reject, that means that that measurement of mu sub 0 is plausible. It exists within the confidence interval. Right, so these things are very closely connected when we're dealing with a two-sided significance test. Right. So I want to make a note of that. The last thing that we can do with our one sample t-test and our inference methods that we've been dealing with in chapter 9 is dealing with inference for means with paired data. This is a way of comparing things. Comparative studies are more convincing than single sample investigations. For that reason, one sample inference is less common than comparative inference. Study designs that involve making two observations on the same individual or one observation on each of two similar individuals results in paired data. When paired data results from measuring the same quantitative variable twice, as in the job satisfaction study, which we may have seen in the past, we can make comparisons by analyzing the differences in each pair. In the conditions for inference, if the conditions for inference are met, we can use a one sample t procedure to perform inference about the mean difference, mu sub d. Right, and so we're using the one sample t procedure on the difference because when we take the difference between those two comparative things, we get a single value. So it ends up being our sample is that difference. These methods are sometimes called paired t procedures. All right. So we will look at an example of this next. I need to make sure to do volume there. All right, so bam. And if you guys can't hear the volume on this, please let me know. I think I have it set up right.
Hi, this is Jason Molesky. Let's take a look at paired data and one sample t procedures. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. Now, during one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took caffeine and the placebo was randomized, and at the end of each 2-day period, a test for depression was given to all 11 subjects. Now, researchers wanted to know if being deprived of caffeine would lead to an increase in depression. Now, this table contains data on the subject scores on a depression test. Higher scores show more symptoms of depression. So we have our 11 subjects here and their depression scores on the first test. We also have our 11 subjects and their depression scores on the placebo test. And then we also have the difference between those scores. And we went placebo minus caffeine because for the most part, the placebo scores are greater than the caffeine scores, and that resulted in positive values for the most part in the difference column. Now, why did researchers randomly assign the order in which subjects received the placebo and caffeine? Well, researchers want to be able to conclude that any statistically significant change in depression score is due to the treatments themselves and not to some other variable. One obvious concern is the order of the treatments. Let's suppose caffeine were given to all the subjects during the first 2-day period. What if the weather were nicer on these 2 days than during the second 2-day period? Well, the researchers wouldn't be able to tell if a large increase in the mean depression score is due to the difference in weather or due to the treatments. Random assignment of the caffeine and placebo to the 2 time periods in the experiment should help ensure that no other variable is systematically affecting the subject's responses. Now let's carry out a test to investigate the question. If caffeine deprivation has no effect on depression, then we'd expect the actual mean difference in depression scores to be 0. That is, the scores when the subjects were on caffeine would be pretty much the same as the scores as when they were on the placebo, so therefore the difference would be 0. So our null hypothesis is that the mean of the differences is 0, while the alternative hypothesis is that the mean of the differences is greater than 0, where the true mean difference is defined by mu sub d, and we did note that that was placebo minus caffeine. Now, because no significance level is given, let's use alpha equals 0.05. Well, to use a paired t-test, let's first check our conditions. We note that the researchers randomly assigned the treatments placebo then caffeine, caffeine then placebo to the subject, so that condition is met. Since we aren't sampling, it's not necessary to check the 10% condition. And when it comes to the normal large sample condition, we don't know whether the actual distribution of difference in depression scores is normal, so we're going to have to do a little extra work here. With such a small sample size, we need to examine the data to see if it's safe to use T procedures. Well, here's a histogram, a box plot, and a normal probability plot of these 11 differences. The histogram itself does have an irregular shape with so few values. The box plot shows a little bit of right skewness, but no outliers here. And the normal probability plot is slightly curved, indicating there is some slight skewness. However, with no outliers and no strong skewness, the T procedure should be pretty accurate. Now, we entered the differences in list 1 and then used the calculator's t-test with the draw command to perform this test. We see our statistic here is 3.53, and we get a p-value of 0.0027. That's the area to the right of t equals 3.53 on the t distribution curve with 10 degrees of freedom. Now, because the p-value is 0.0027, and that's significantly less than 0.05, we reject our null hypothesis. We have convincing evidence that the true mean difference, placebo minus caffeine, in depression score is positive for subjects like these. Now, for some additional practice with paired data and one sample T procedures, try exercise 85.
Are there any questions about this example? Anything you'd like me to review? So lastly, we need to make sure that we are using our tests wisely. Carrying out a significance test is often quite simple, especially if you use a calculator or a computer. Using tests wisely is not so simple. Here are some points to keep in mind when using or interpreting significance tests. You want to consider how large of a sample do you need. All right, a smaller significance level requires stronger evidence to reject the null hypothesis. A higher power gives a better chance for detecting a difference when it really exists. At any significance level and desired power, detecting a small difference between the null and alternative parameter values requires a larger sample than detecting a large difference. Okay, so a larger sample helps us detect something that's, if the null and the alternative are really close in value, right? We can detect that better if we have a larger sample. Statistical significance and practical importance. When a null hypothesis, no effect or no difference, can be rejected at the usual levels, there is good evidence of a difference, but that difference may be very small. When large samples are available, even tiny deviations from the null hypothesis will be significant. Okay, and we need to decide, is that really significant? Like, in the whole grand scheme of the thing we're testing, does that significance matter? Is it really important? And beware of multiple analyses. Statistical significance ought to mean that you have found a difference that you were looking for. The reasoning behind statistical significance works well if you decide what difference you are seeking, design a study to search for it, and use a significance test to weigh the evidence you get. In other settings, significance may have little meaning. So essentially this is saying if we continue kind of testing the same thing, but like redesigning our study to help find that difference, and so we have multiple analyses of the same test, so to say, that becomes watered down, right? Because we've redesigned the test so that we find the thing we're looking for, whether we did it on purpose or, or not. And that's the end of chapter 9. And if you need to access these slides or these notes, you can find them in the 9.3 Desmos activity. All the notes and examples are right in here. Right. Now, is there anything you guys would like me to go over from chapter 9 before we move into the chapter 10 notes for today? Alrighty. Then we're going to start. Again, if you have something you're taking notes on, you should be ready. There's going to be some things you're going to want to probably write down. All right, so here we go, starting chapter 10, comparing two populations or groups. This is different than what we just talked about from chapter 9 with the paired data, because this is having to do with comparing separate populations or separate groups. With the paired data, where those observations are coming from most likely the same population or the same group. Okay. So this is two different or separate populations or groups. And in section 10.1, we're comparing two proportions. 10.2, we'll be comparing two means. So for this lesson, we're going to learn how to describe the shape, center, and spread of the sampling distribution of the difference of two sample proportions. Remember, sampling distributions goes back to chapter 7. We're going to determine whether the conditions are met for doing inference about P1 minus P2, proportion 1 minus proportion 2. Right. And our conditions are throughout chapter 7, 8, and 9. It's our random 10% and large counts. Construct and interpret a confidence interval to compare two proportions. That goes back to chapter 8. And perform a significance test to compare two proportions. That is chapter 9. Right, so we're kind of tying all these things together. We're using the same concepts and modifying those formulas to deal with comparing two things. Right, so suppose we want to compare the proportions of individuals with a certain characteristic in population 1 and population 2. Let's call these parameters of interest P1 and P2. The ideal strategy is to take a separate random sample from each population and to compare the sample proportions with that characteristic. Right, so it's like maybe we wanted to do something about the proportion of people in two different schools, right? Those would be two separate populations who are left-handed. Right? The left-handedness is the characteristic that we are interested in. Right. What if we want to compare the effectiveness of treatment 1 and treatment 2 in a completely randomized experiment? This time the parameters P1 and P2 that we want to compare are the true proportions of successful outcomes for each treatment. We use the proportions of successes in the two treatment groups to make the comparison. Right. In this scenario, we could be running an experiment, which the experiment could be conducted within a certain population. And then we want to know essentially which treatment was more effective. Right, so we get results from treatment 1, we get results from treatment 2. They both have a certain proportion of success. Right, P1 and P2, and then we use some of these inference methods to decide which one was better. Right, so we have two different scenarios where this type of these types of procedures will apply. Right. And here's the notation that goes along with this. We have population or treatment 1 gets parameter P sub 1, statistic P hat sub 1, and sample size N1. So the subscript for each of these refers to which population or treatment it belongs to. Right? These things will need to be defined when you use them. Right? Population treatment 2 is P2, P hat 2, and N2. Right. Does anyone need a moment to write any of this down? Raise your hand. All right. All right, so here we have a scenario, all right, for our sampling distribution. To explore the sampling distribution of the difference between two proportions, let's start with two populations having a known proportion of success. If we remember, when in chapter 7, dealing with sampling distributions, to do these procedures, we need to have a known parameter P. Right, chapters 8 and chapters 9, we don't know what the true proportion will be, so we have our inference methods to use. In this case, we're just finding the sampling distribution and finding the shape, center, and spread. All right, so at school 1, 70% of students did their homework last night, and at school 2, 50% of students did their homework. Right, and these are within the population. Suppose the counselor at school 1 takes an SRS of 100 students and records the sample proportion that did their homework. School 2's counselor takes an SRS of 200 students and records the sample proportion that did their homework. Notice that we don't need the same size sample. Right? N1 and N2 don't need to be the same. What can we say about the difference? P hat 1 minus P hat 2, the sample proportion from population 1 and the sample proportion from population 2. What's their difference? Right, using Fathom software, which is a statistical modeling software that's we don't have access to, but the publishers do. We generated an SRS of 100 students from school 1 and a separate SRS of 200 students from school 2. The difference in sample proportions was then calculated and plotted. We repeated this process 1,000 times. So this again goes back to chapter 7 in our sampling distribution. We're repeating the same sampling over and over and over again, and we get this distribution. Right. So we have the approximate sampling distribution for P hat 1, approximate sampling distribution of P hat 2, and approximate sampling distribution of P hat 1 minus P hat 2. And we get shape, center, and spread for each of these, right, based on those distributions. Right. And if we remember from chapter 7, the mean of the sampling distribution of the sample proportions is equal to the population proportion, which is 0.7. We get 0.5 for school 2, and the difference is 0.2, 0.7 minus 0.5. We get the spread, right? This is the, under the square root sign is the variance, right? Which is how we calculate that. We have population proportion 1 times 1 minus population proportion 1 divided by n1, square root of that, we get the standard deviation. We get 0.0458, we get 0.0354 for population 2, and the difference is 0.058. We'll get into how these are calculated later. So this is our sampling distributions, at least what they look like. What do we notice about the shape, center, and spread of the sampling distribution of P hat 1 minus P hat 2? Essentially, it's still normal, right? Which is good news, right? And we have our center and spread that are definitely related to the center and spread of the other two distributions. Right, we'll get this put together in a moment. So both P hat 1 and P hat 2 are random variables. And this ties back into chapter 6 now. The statistic P hat 1 minus P hat 2 is the difference of these two random variables. In chapter 6, we learned that for any two independent random variables, x and y, which in this case is P hat 1 and P hat 2, the mean of the difference of those two random variables is the mean of x minus the mean of y. And the variance, notice this is variance, this is not standard deviation. The variance of the difference between x and y is the variance of x plus the variance of y. And this is one of those things that was slightly different when we were learning these. The difference of the variance of the difference of two random variables is the sum of those two variances. Okay. So the sampling distribution of the difference between two sample proportions, right? When we have an SRS of size N1 from population 1 with proportion of success P1 and an independent SRS of size N2 from population 2 with proportion of successes P2, the shape when essentially the large counts condition is satisfied. So there's at least 10 successes and 10 failures in population 1 and at least 10 successes and 10 failures in population 2. The sampling distribution of p hat 1 minus p hat 2 is approximately normal. Center, the mean of the sampling distribution is p1 minus p2. So population proportion 1 minus population proportion 2. And lastly, the spread, right, the standard deviation of the sampling distribution of p hat 1 minus p hat 2 is the square root of p1 times 1 minus p1 divided by n1 plus p2 times 1 minus p2 divided by n2. As long as each sample is no more than 10% of its population. That's our 10% condition. So when doing the sampling distributions, we have to check the large counts and 10% conditions. And there's only two conditions that we test for sampling distributions. Does anyone need a moment to write this down? And we have this in a visual. Right? We have our normal curve essentially here. We have our sampling distribution is the curve. Right? This curve here, that's our sampling distribution. All the values of p hat 1 minus p hat 2 are on the essentially horizontal axis. The mean is in the center and the standard deviation, well, is our standard deviation. It helps us determine how wide or narrow our distribution is. All right, so here we have our same context about our schools. All right, school 1 is 70% of their students did their homework. Only 50% of students at school 2 did their homework. We have school 1 has an SRS of 100. School 2's SRS is 200. And they're going to record the proportion that did their homework from those SRSs. They're going to describe the shape, center, and spread of the sampling distribution of the difference. Okay, so because there are 70 successes and 30 failures in population 1 and 100 successes and 100 failures in sample 2, population 2, so they're both at least 10, the sampling distribution of p hat 1 minus p hat 2 is approximately normal. This comes first because then that allows us to find mean and standard deviation based on a normal distribution. Its mean is p1 minus p2, which is 0.7 minus 0.5, we get 0.2. And the standard deviation is the square root of 0.7 times 0.3 divided by 100 plus 0.5 times 0.5 divided by 200, and we get 0.058. Okay, so we have now described the shape, center, and spread of the sampling distribution. All right. So that's how we do sampling distribution for the difference between two proportions. Next, we're going to look at the confidence interval for the difference between two proportions. Does anyone need a moment to write anything down from this screen before we move on? So our confidence intervals for P1 minus P2 when data come from two random samples or two groups in a randomized experiment. The statistic P hat 1 minus P hat 2 is our best guess for the value of P1 minus P2. So now remember, in confidence intervals, we do not know what the population parameter is. We're trying to guess. we can use our familiar formula to calculate a confidence interval for P1 minus P2, statistic plus or minus the critical value times the standard deviation of a statistic. When the 10% condition is met, the standard deviation of the statistic P hat 1 minus P hat 2 is the square root P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 divided by N2. And this is the same exact formula we saw essentially on the previous thing about sampling distribution. However, recall, we don't get to use P1 and P2 in this case, and we'll see, again, that's because we don't know them when doing confidence intervals. If the normal condition is met, we find the critical value Z star for the given confidence level from the standard normal curve. And again, we have our conditions. Random 10% in large counts. But in this case, we need to check these three conditions for each population. Random 10% in large counts for population 1, random 10% in large counts for population 2. All right, we must make sure that both populations are satisfied. And then, as I said previously, because we don't know the values of parameters P1 and P2, we replace them in the standard deviation formula with the sample proportions. The result is the standard error of the statistic P hat 1 minus P hat 2, which is the square root of P hat 1 times 1 minus P hat 1 divided by N1 plus P hat 2 times 1 minus P hat 2 divided by N2. All right, which leads us to our inference method. Would anyone like a moment to write anything down from this screen? So we have our two sample Z interval for a difference between two proportions. This is the inference method in this chapter for proportions. When the conditions are met, an approximate C% confidence interval for P hat 1 minus P hat 2 is P hat 1 minus P hat 2 plus or minus Z star times the standard error, square root of P hat 1 times 1 minus P hat 1 divided by N1 plus P hat 2 times 1 minus P hat 2 divided by N2, where Z star is the critical value for the standard normal curve with C% of its area between negative Z star and Z star. And again, we find that Z star value by using table A. Right? And it depends on the confidence level, like the percent. We use that when we go into table A and follow that back out to the Z score that corresponds with that proportion. We'll see examples of this, not today, but next week. It will all make sense. Does anyone need a moment to write this down? All right, so this is how we will construct confidence intervals. And now we'll move into the chapter 9 part of this, which is significance tests for P1 minus P2. An observed difference between two sample proportions can reflect an actual difference in the parameters, or it may just be due to chance, variation in random sampling, or random assignment. Significance tests help us decide which explanation makes more sense. The null hypothesis has the general form H0 such that P1 minus P2 equals the hypothesized value. We'll restrict ourselves to situations in which the hypothesized difference is 0. Then the null hypothesis says that there is no difference between the two parameters. Right, so essentially the default is that the null hypothesis says that the proportion of population 1 and population 2 are the same for whatever we're curious about, or if it's an experiment, the results of treatment 1 and the results of treatment 2 will be essentially the same. Right, so we get H naught such that P1 minus P2 equals 0, or we can write it that H naught such that P1 equals P2. Okay, either writing of this will be okay. The alternative hypothesis says what kind of difference we expect. Either the alternative says that the difference between the two is greater than 0, so we'll end up with a positive number. The difference is less than 0, we'll get a negative number. Or that it's just not 0, right, which would be a two-sided test. All right, and depending on what we're curious about, what claim we're testing, depends on whether or not we're going to do greater than 0, less than 0, or just not equal to, and that is very similar to what we did in the previous chapter. And again, we have our conditions, and these are the same 3 conditions again that we used in chapter 8 and chapter 9, and for confidence intervals. We have random 10% and large counts. Again, 10% is when sampling without replacement. We'll get back to why we're highlighting that again in a moment. But once more, you must check these 3 conditions for both populations or both groups. Okay. Then to do a test, we standardize p hat 1 minus p hat 2 to get a z statistic. Right? We have the test statistic equals statistic minus parameter divided by the standard deviation of the statistic, which in this case will have z equals p hat 1 minus p hat 2 minus 0, because we're defaulting to when there is no difference, divided by the standard deviation of the statistic. Right? If the null hypothesis is that p1 equals p2 is true, the 2 parameters are the same. We call their common value p. We need a way to estimate p, so it makes sense to combine the data from the 2 samples. This pooled or combined sample proportion is p hat c equals count of successes in both samples combined, divided by the count of individuals in both samples combined. So x1 plus x2 divided by n1 plus n2. Now we need this pooled or combined sample proportion to use in calculating our standard deviation of the statistic for our z statistic, which comes here. All right, so suppose the conditions are met. And this is our inference method for our significance test for the difference of population proportions. To test the hypothesis H not such that P1 minus P2 equals 0, first find the pooled proportion P hat C of successes in both samples combined, and then compute the Z statistic. Right? We use that pooled proportion in calculating our Z statistic. We use that the same way that we used the null hypothesis proportion in chapter 9. Right? So we have Z equals P hat 1 minus P hat 2 minus 0, divided by the square root of P hat C times 1 minus P hat C divided by N1 plus P hat C times 1 minus P hat C divided by N2. In both of these, you have the same numerator. The denominator is just the different population sizes, or sample sizes, sorry. We then find the p-value by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternative hypothesis. At this point, essentially, we use that p-value the same way we did in chapter 9. Right? We look at the direction of our alternative and then find the proportion under the curve greater than, less than, or we find one side and double it for the two-sided test. All right. And so then that is our 2 sample z-test for the difference between 2 proportions. Would anyone like a moment to write this down? So many important statistical results come from randomized comparative experiments. Defining the parameters in experimental settings is more challenging. Most experiments on people use recruited volunteers as subjects. When subjects are not randomly selected, researchers cannot generalize the results of an experiment to some larger populations of interest. Researchers can draw cause and effect conclusions that apply to people like those who took part in the experiment. Unless the experimental units are randomly selected, we don't need to check the 10% condition when performing inference about an experiment. Right. So there are times that we can omit checking the 10% condition, and that is when we are conducting an experiment, right? And the experimental units, the people participating, were not randomly selected. Okay, so there are special conditions that apply. But again, that also affects what kind of conclusion we can make, whether it's about the whole population or not. That's the end. All right, so this is the notes portion, essentially, for section 10.1. Right, these are the formulas, these are kind of the rules and everything that we will be using. So I wanted to do that first. Tomorrow we'll see the similar kind of stuff for section 10.2. Next week we'll do practice. And this should also help us practice some of the concepts from the previous chapters as kind of like a review-ish kind of thing. All right. Does anyone have any questions, comments, concerns about what we've just gone through or anything else? All right, I know that was a lot. I know it came at you guys pretty fast, so hopefully we can just kind of let that settle. And maybe you guys will have other questions. If you do have any other questions, comments, concerns, please make sure to let me know in some way. Other than that, that is all that we have for today. I hope you have a great rest of your day, and we will see you tomorrow.